There are going to be four factors that we look at when we are considering an NMR spectrum, and the first of those is what we call the chemical shift. In the last video, we talked about the NMR spectrometer picking up on emissions in the radio frequency range during the relaxation process, and of course those emissions are in megahertz. But if we were to give the data in megahertz, and then we went to another instrument with a different size magnet, you wouldn't be able to compare the numbers, because remember, there's a relationship between magnetic field strength and the frequency. So you have to have a way to normalize the data so that you can compare it from one instrument to another. And we use an internal standard for this. So the standard that we use is tetramethylsilane. And we set this, the signal that's generated from the protons on tetramethylsilane, so these guys here, we're going to set that signal to 0. And then the signal for all of the other protons that happen to be in the sample are going to be measured with respect to TMS. So you're actually going to take the distance in hertz, and then you divide out the strength of the instrument in megahertz. And then that gives you what's called the chemical shift, which is in parts per million. And that way you can compare data from one instrument to another. We represent the chemical shift with the lowercase delta symbol, so you might see these used interchangeably. Delta, ppm, chemical shift, they all have the same meaning. Here's what an actual NMR spectrum looks like. This is very simple. This is just methane, and it gives one signal, and that signal is showing up at 0.232 ppm. We're, just like with IR, increasing in energy from right to left. So we would say that this is higher energy down here, and this is lower energy over here. And there's some other terminology that needs to be introduced here. As we go from right to left, we say that we're going downfield. And as we go from left to right, we say that we're going upfield. And then the chemical shift, which is the ppm here, notice that it's increasing from right to left. And so we would say that we're getting a higher chemical shift over here and a lower chemical shift on the right. As far as the spectrometer is concerned, all four of these H1 nuclei look the same. So they're all going to give one signal. And when I say look the same, I mean that they are spending their time in the exact same chemical and magnetic environment. So let's look at something like this with dimethyl ether and see if we can decide if all of the protons on this structure would be identical. This goes back to looking for symmetry like we did when we studied stereochemistry. And if you take a look, you see that this is a symmetrical molecule, and so there's no reason that the three protons on this side would be spending their time in any different type of environment than the three protons on this side. All of the bonds are going to be exactly the same, the orientation in space and everything. So we would only predict one signal from this compound. And here's the proton NMR spectrum of dimethyl ether, and you see, yes, there is only one signal. But if you look at the placement of the two signals, methane and dimethyl ether are not in the same position. And so we need to use our new terminology to describe their relative positions. We would say that this signal coming from the dimethyl ether is downfield from this signal here. Conversely, we would say that this signal here is upfield from the dimethyl ether signal. In the next video, we're going to talk about why these signals are appearing at different chemical shifts.